Reef carbonates are, perhaps more so than level bottom sediments, the interface between biology and carbonate sedimentology, since reefs are fundamentally constructed by living organisms. In terms of volume of sediment, reefs are fairly minor components of global carbonate deposition. However, reefs are extremely important oil and gas reservoirs rocks due to their high porosity typically. So the geological definition of a reef may differ from other fields, like the biological definition of a reef, for example. Geologically, a reef must be a rigid, wave-resistant structure. It must have bathymetric relief above the seafloor, or it must stick up above the seafloor. And finally, it must be formed in place by growth, trapping, or binding of sediment by organisms. So what that means is that a reef can't just be a pile of sediment built up by energy. It has to be built there in place by organism activities. In today's oceans, nearly all reefs are built in shallow tropical waters by corals, but it hasn't always been this way. Sponges and other types of organisms have been reef builders at different times in the geological record. So we're not going to focus on the biological aspects of who's building the reefs in this video, but we are going to focus on the sedimentological aspects, the reef components, and the reef processes, and ultimately the types of sediments you get in and near the reef. So the formation of a reef is a balance between constructive processes, producing or trapping sediment to build the reef structure above the seafloor, and destructive processes, which is breaking the reef apart and converting it back into sediment ultimately. The main constructive process in a true reef is the growth of an organic framework, which is built from the skeletons of the organisms like the corals or the sponges. Binding of sediment and binding of the framework itself by encrusting organisms, and the trapping or baffling, as it's called, of sediment by platy or fan-shaped organisms can also be important. So given these processes, reef limestones can be composed of framework, which is the organism skeletons that built the rigid structure. So in this Devonian reef here, those organisms are actually also corals, among other things, also sponges, but I've illustrated a few corals here with the light blue arrows that are responsible for contributing to the framework construction. Encrusting or binding algae or microbes or even animals can also be important. In this reef, the sort of speckly or mottled or clotted, it's often called, textures that are indicated here by the red arrow are areas of microbial binding. There can also be platy baffling organisms, which are not really shown well in this example, as well as cavities, like this here, which are open void spaces within the reef framework that can be filled with sediment or with cement, or which can remain as open void spaces, like in this slab right here. So microbial binding was much more dominant in reefs of Proterozoic through Triassic age, and this lower Cambrian reef here contains a framework constructed of a type of sponge called archaeocyathes. So here are some of the archaeocyathes with the circular or cylindrical features in this rock. There is, again, abundant clotted binding by a microbial structure called rhenalsis, as well as cavities filled with sediment, as well as with cement at the top of the cavities. So here's a Permian example of a reef where baffling organisms dominated. So the spiral sort of platy features that you can see highlighted a few places by the blue arrows are platy algae that trapped sediment, the light brown areas, and then the void space in between the algae was mostly filled with concentric layers of cement. So a true reef must have a rigid framework built by organism skeletons, but there are also large structures that have relief above the seafloor that are basically just mud. And these are called mud mounds, and they're dominated by mud that was presumably trapped by baffling organisms or bound by microbes. So microbial activity was likely important in a lot of mud mounds, as suggested by the clotted appearance of the muddy texture here. So both reefs, or true reefs, as well as mud mounds, are types of a broader category called a bioherm. A bioherm is just an unbedded, organism-built structure with relief above the seafloor. So it's slightly more inclusive. It can include, so bioherms can include reefs that have a framework built by organisms, as well as mounds that have relief but no framework, so they are dominated by binding or baffling. So reef cavities are also commonly filled by cement, which indicates that they were open void spaces as the reef was buried and lithified. So in the photo here, again, the blue arrows point to a few of these frame-building archaeocyath sponges, and the green arrow shows you a large cement and sediment-filled cavity. More generally, cementing and binding of the reef framework itself plays an important role in the rigid nature of the reef. This allows the reef to have these steep, wave-resistant profiles that characterize bioherms in general, but reefs in particular. So one last picture, just of another reef. This Permian reef here was built by different types of sponges. The blue arrows, some of these cylindrical and circular oval features. But it also has actually some pretty impressive radiating crystals of cement. The green arrow shows one of these crystals as it radiates out to the right from that point that were growing into one of these reef cavities. So those constructive processes of framework building, sediment baffling, and sediment binding are always in a race against the destructive processes. Reefs are primarily shallow water features, so wave energy, especially large storms like hurricanes, can damage the reef. Bioerosion, which are the destructive activities of boring and eroding organisms, has become an increasingly important destructive process in the Mesozoic and the Cenozoic in particular. And there can also be a feedback between bioerosion and wave energy, where bioerosion weakens the reef by undermining or eroding away the coral parts or the framework parts, and that makes the reef as a whole more susceptible to physical wave breakage. So bioerosion is performed by many types of organisms, including the bivalves whose borings are shown here, these sort of cylindrical smooth features, but also by sponges or sea urchins or parrotfish or many other types of organisms. Reefs have a unique stratigraphic expression. They show up as these large, unbedded blobs of carbonate in otherwise layered or bedded strata. They're unbedded because of their construction from an irregular organism framework. The organisms are building on top of one another. They don't actually form layers like you would get in a normal sediment. Both true reefs as well as mud mounds have relief above the seafloor, so what this means is that if you look at a large section, the surrounding beds will onlap, which means they thin and drape over the unbedded reef core. And because reefs have this rigid framework that gets cemented and bound together on the seafloor, they can produce steep or even vertical fore-reef slopes at the edge of the carbonate platform. Their rigid structure also means that parts of the reef can break off as large, intact blocks and fall down the reef slope into the deeper parts of the basin. So as a result, fore-reef deposits are often quite coarse-grained, despite their deep water setting, and they may even contain these disorganized breccias of large blocks of reef talus. And so, despite the deep water environment that they're deposited in, because of gravity essentially, and the lithified nature of the reef, the fore-reef is likely to have typically coarse-grained and perhaps disorganized sediments.